Live from beautiful Brigham Young University in the Benson Building. This is Chem 351. I sent out an email earlier today about the exam, which most of you have taken. There's still a few exceptions slash accommodations in the works, so I won't talk about specific exam questions right now. When the rest of the exams are in, I will make it possible for you to view items missed and what your responses were and what the correct answers are. As with last time, I will post on YouTube a video of me going through each and every question. I'll post them by question so you don't have to filter through the file and try to find it. And that should happen soon, probably by Wednesday. I can tell you at this point that the average on the exam was a bit higher than it was last time, so I congratulate all of you. The email contains some details about putting your particular exam score in context. Some of you may wish still to talk about specific items on the exam or your how your study process can improve, and I'm happy to do that. Later today, I will send out a link to a Google Sheet like we did last time with some specific times available when we can meet either via Zoom or in person. And until then, if you have specific questions, feel free to send me an email. I'm behind a little bit on emails over the weekend. There's a few I haven't had a chance to respond to yet, but I will get caught up later today. All right. So I think I said this last time too, but it's just like the scene in Elf where Santa Claus says we've had a very successful Christmas and now it's time to start preparations for next Christmas. And here we are again starting preparation for the next exam. We're not quite through with chapters 7 and 8. Probably today and Wednesday will be all we'll do there. And today we're going to pull back the curtain on the complexity that has been sort of hiding in the periphery as we have just focused on substitution reactions. So to see what the problem is, we're going to review what we've said before about carbocations and then extend it to alkyl halides in general. Recall that because of hyperconjugation, we've said that the LUMO of a carbocation is actually delocalized onto adjacent carbon-hydrogen bonds as well. So here's the positively charged carbon. I'm only going to draw maybe 3 of these carbon-hydrogen bonds out specifically. I'm going to draw the empty p orbital on the positively charged carbon. I'm going to draw in the phases as we've done previously. And then going to remind you that because of sigma to p hyperconjugation between the empty p orbital and the filled sigma bonds adjacent to it, that we actually have a LUMO that looks like this, where some of the LUMO, most is still on the positively charged carbon, but some is on those adjacent carbon-hydrogen bonds. I don't believe I've ever drawn it this way before in class. I've usually just focused on one of the carbon-hydrogen bonds. But I want to point out that in the carbocation, the LUMO is on the positively charged carbon and on, remember our new way of talking about carbons in alkyl halides, and carbocations. We've got the alpha carbon, which is the one that has the positive charge, or the alkyl halide, and then the beta carbon, which is the one adjacent to it. The LUMO is on both the positively charged carbon and on the beta protons. Okay, is that sounding familiar? We talked about that. That's the whole reason why carbocations that are more substituted are more stable. But The challenge here that we haven't considered, though I've alluded to it, is that a molecule with a highest occupied molecular orbital, usually lone pairs on a heteroatom, we'll just draw it like that, now has a choice. Do we attack at the beta hydrogen, the beta proton rather, or do we attack at the positively charged alpha carbon? We're going to say that attacking at the positively charged alpha carbon is the preference of a nucleophile, whereas attack at the beta proton is the preference of a base. Or in other words, nucleophiles attack carbon, bases attack hydrogen. All right, and this will be an issue for us from this point on for every carbocationic intermediate or every alkyl halide. Is the particular molecule I'm using going to be a nucleophile, a base, or both? And we're going to see that there are molecules that fall nicely into both categories, so they could do both. They could either attack at carbon or the beta proton, and then there are other molecules that will only do one versus the other. So keeping track of how that happens is going to be the most challenging part of the next couple of lectures. And we will talk today about what makes a good nucleophile good, what makes a good base good. But for now, let's just think of the molecules that we're using to attack these carbocations or alkyl halides as some nucleophile and or base, because the same molecule can have both characteristics. Questions you want to ask so far? Okay.
Does it matter which beta, like, are all three of those carbons beta, or is it just one?
Yeah, that's a good question from our audience at home. All of those carbons that are adjacent to the alpha carbon could be considered beta carbons. And this is an important complication because in the example I've shown you, each of those beta carbons is identical. That's on purpose, but we will quickly get to examples where there are different kinds of beta protons on different adjacent alkyl groups, and we will need to decide what the outcome is. In this case, it doesn't matter whether you attack the one I've shown or the other two, they're all the same. But yeah, we will see that there are different kinds of beta protons, and we'll have a fundamental way of talking about which one leads to the major product. Yeah? Does having a better base or a better nucleophile make the reaction happen faster? For E2 and SN2 reactions, yes. SN1 and E1 don't depend on the nucleophile, so technically not, though I suppose if you have a stronger base / nucleophile, the likelihood that it's going to wait around for SN1 versus E1 instead of doing something else gets lower. So what we're going to do eventually, you'll recall how last time or in the previous lectures, we sort of considered primary, secondary, tertiary alkyl halides, and then SN1 versus SN2. What we're going to do is, from here on out, once we talk about what makes a good nucleophile good, we're going to interweave characteristics of good nucleophiles and good bases versus things that are good nucleophiles but weak bases. And we're going to consider what the combination of that kind of nucleophile and base with that kind of alkyl halide does. And we'll be able to reason our way through it. Other questions? Okay, so the issue with a delocalized Lumo is also true for alkyl halides. So to see this, we're going to take a very simple example of say, a secondary alkyl halide. So how would we do this? Let's put a bromine here. And then, yeah, let's have two adjacent carbon-carbon bonds. And then let's have them in this simple example, let's have them both be methyl groups. All right. So again, you have an alpha carbon, the one that has the leaving group, and then we have beta carbons. And it just so happens that in the example I've chosen to show you, the beta carbons are both the same. All right, now in an alkyl halide, normally we would have described the LUMO as being the carbon halide sigma star, which to draw would have looked like this, sort of smaller lobes pointing inward to where the node is and larger lobes on the outside away from the area where the node is. I'm going to color in the wave function sign relationship so that you can see where the nodes are. For this sigma star, we have a node at bromine, a node at carbon, and a node in between the two nuclei, and that's how we identify it as a sigma star. But the situation for alkyl halides is a lot similar to the situation for carbocations. That is, you've got adjacent filled orbitals that can line up with the empty sigma star. So I'm going to draw how that could be. Here is one of those adjacent sigma bonds. Here is another one of those adjacent sigma bonds. And hyperconjugation happens here. The filled carbon-hydrogen sigma bond mixes with the empty carbon-bromine sigma star. This allows the electrons in the carbon-hydrogen bond to go lower in energy and delocalize a little bit. At the same time, it makes the LUMO go higher in energy but spread out a little bit onto those adjacent protons. And if we did the calculations, this is what the LUMO would look like. Again, what we're referring to with hyperconjugation is this idea that a filled molecular orbital in a molecule can overlap with an empty molecular orbital in a molecule, and they can mix together. You get the plus combination and you get the minus combination as we've done previously. This is the, oh, sorry, I got ahead of myself in writing this down. What I've drawn for you here is that minus combination. This is the LUMO for this molecule. And this has the effect of moving the electrons from the original carbon-hydrogen bond down in energy, so it's stabilizing, and it has the effect of moving the LUMO out onto the beta proton. So LUMO is at the alpha carbon and on beta protons. Okay. One other way to see this, I'm not sure, I think maybe we won't draw it this way, but if you wanted to, no, actually we're going to draw it this way, sorry. So this means that the nucleophile slash base with the high energy electrons, again, can choose whether to attack at the alpha carbon and do SN2 chemistry, or to attack at one of the beta protons and do a reaction we call elimination. Same thing as we said above. We're going to see that good nucleophiles attack the alpha carbon, whereas good bases attack the beta hydrogen, or the beta proton. One other thing that's important, it's a nuance that's actually embedded in this idea of hyperconjugation, but I want to point it out because it may not be obvious. Hyperconjugation only works, the LUMO only spreads out onto beta protons that can line up with the sigma star. Okay? And this is what we've talked about before, side-by-side overlap for orbital mixing works best when orbitals are parallel or lined up with each other, not perpendicular. Man, terrible penmanship. What do we mean by lining up with each other? Well, let's put ourselves in close to where this molecule is, and let's look down the bond between the beta carbon and the alpha carbon, and let's draw a Newman projection. Here is the beta carbon. The alpha carbon is back there. We can't see it. If we were looking down that carbon-carbon bond, we'd have a hydrogen sticking out here, and another there, and another there. And then in the back on that alpha carbon, we would have a bromine pointing to our right, a hydrogen angled down to our left, and then another methyl group pointed up to our left. See where I'm getting this? You got the idea of where we're looking at the molecule. A model may be helpful if this is challenging to see. Notice that from our drawing, the beta proton that has the LUMO on it is anti to the leaving group. The beta proton that has the LUMO on it is anti to the leaving group. I'm going to draw the orbitals again on this Newman projection. We won't be able to see all of them. This is the sigma star on that alpha carbon. Some of the orbital, I guess I better keep the phase the same to be consistent. We've got orbital density in between the two nuclei, between the alpha carbon in the back and the bromine. There's a node in between them, and then the lobe, the other lobe on the sigma star sticks out on the other side of the alpha carbon. And I'm just going to color the phase in yellow, and that's for the sigma star in the back. Then if we were to draw the sigma, the carbon hydrogen sigma in the front, or the portion of the LUMO rather that is on that carbon hydrogen sigma, we would do so like this. And what we see is that the LUMO is only on the beta proton that is anti to the leaving group. Yes?
So in this you do them out of phase with each other. Is that how it would be to make it work, or would they have to be?
Well, that's a good question. I've drawn them out of phase with each other. The reason I did that is because I am drawing the LUMO, which comes from the out of phase or minus combination. If instead we were drawing where these electrons were, they would be in phase with each other. So I'm just drawing the LUMO the way it looks. It turns out whether or not the orbital's the same phase on the beta hydrogen versus the alpha carbon is not going to have any practical implications. So it's not a point to worry about too much. I'm just, I guess, trying to be realistic. Go ahead. Would we also see hyperconjugation between which carbon and bromine? the carbon-bromine sigma bond and the carbon-hydrogen sigma star? Yes, you would see hyperconjugation between the carbon-bromine sigma bond and the carbon-hydrogen sigma star, though probably those two are far apart, even farther apart in energy than the carbon-hydrogen sigma bond and the carbon-bromine sigma star. So it may not make that big of a difference. All right, there's a lot of questions on the chat that are actually getting ahead of where we are. So let me see if I can address them. Ben, you asked whether because the bond between beta carbon and alpha carbon can rotate freely, then can any of those three protons at a given point be anti to the leaving group? Yes. Okay, so because that methyl group is doing propeller action all the time, we're shifting through which proton is anti to the leaving group, but at any given point, one of them could be. And we'll talk about how you're going to see that the requirement that the proton you remove be anti to the leaving group is going to have some important implications for the stereochemical outcome of this reaction. But I think I'll be able to answer those questions a little bit better once we've talked about what the elimination reaction is. That being said, yes, if the nucleophile attacks the alpha carbon of this alkyl halide, then that is the SN2 reaction. If it attacks at the beta proton, that is the E2 reaction. Attack at the alpha carbon leads to substitution products, and attack at the beta hydrogen leads to elimination products. Okay, other things I've missed here in class or at home. So this is a key point. The LUMO is only on the beta proton that is anti to the leaving group. And that means there's this requirement that we're going to call, that you're going to see in the text. Anti to the leaving group, your text is going to call that anti-periplanar, which is a fancy way of saying that the dihedral angle between the two bonds, the carbon-hydrogen, beta carbon to hydrogen bond and the alpha carbon to bromine bond, the dihedral angle is 180 degrees. But that requirement, which is given in your text as a rule, flows naturally from what's going on to put the LUMO on the beta proton in the first place, which is hyperconjugation, which can only happen when they line up with each other in that way. All right. Questions? So let's just show you what the consequences are for attack at the beta proton versus attack at the alpha carbon. And let's start with the carbocation. I'm going to copy some of this and then erase it. So reaction consequences. Erase, erase, erase. All right. If we attack at the alpha carbon with your nucleophile / base, that leads to what we would call an SN1 product if we attack that carbocation. And again, we're going to remember that this can happen from above or below, like we talked about last time. SN1 product, not production. I don't know what I'm saying there. We would make a new sigma bond because we're going to get end-on-end overlap between the lone pair electrons on the nucleophile and the portion of the LUMO that is on the alpha carbon. And we make a sigma bond. All right, that's straightforward. You've already been there. Now let's talk about attack at the beta proton. And to see how this happens, to see what happens here, it may be useful to not only think about the minus combination of the carbon hydrogen sigma star on the beta proton with the empty p orbital, but also to consider what the plus combination looks like. This is what is happening to those electrons in the carbon hydrogen bond because of hyperconjugation. The plus combination looks something like this. You have carbon hydrogen, maybe for the sake of our discussion, we're going to ignore those other carbon hydrogen bonds because I don't want us to get focused on the wrong things. So, as it says in the Doctrine and Covenants paraphrase, what I say unto one beta proton, I say unto all. What we say here will apply to all of them. That was lame. I didn't try it at home this weekend, but I'm pretty sure it would have gotten not a great response. Hey, actually, Home Center Church in the Price family went well this weekend because Dallin woke up with sniffles on Saturday, so we quarantined him in his room because we thought there might be a risk of COVID. There wasn't. We had him tested this morning and he's fine. But he was in his room, and then Adam woke up on Sunday morning with a bit of a sore throat, so we quarantined him in his room. So Home Center Church was just me and Amber and the two older kids down in the living room, and we let the younger children zoom in from upstairs. But we were able to mute them and disable their chat functionality as necessary. And so it went great. Adam actually was excited to participate from there. Dallin was saying rude words through the chat until I silenced him, but at least he was upstairs and away from us. So we'll see. Maybe we'll have to do that more. Time for church. Everybody go to your rooms. Where were we? Oh, yeah, failed jokes and all of that stuff. Anyway, this is what the plus combination looks like, where the electrons in the carbon-hydrogen bond are partially delocalized toward where the empty p orbital is. And, you know, if you look at that and think, what if I made it so that these electrons were evenly shared between those two carbons? That would look pretty much like a pi bond, right? Because of hyperconjugation, the electrons that are in the carbon-hydrogen bonds are already in a wannabe pi sort of relationship between the beta proton, well, between alpha and beta carbons. Now, because some of the Lumo is out on that beta hydrogen is more acidic than you would expect for a regular carbon-hydrogen bond, and so your nucleophile / base could attack the Lumo at the beta proton. When that happens, the electrons that used to be in the carbon-hydrogen bond actually shift over to become, and you know, we can draw the mechanism from either of these orbitals, but the electrons from that carbon-hydrogen bond actually shift over after the reaction. That beta proton is now on your nucleophile, and the only thing that's changed as far as the electrons that were in that beta, shared between the beta carbon and the beta proton, the only thing that's changed is now they're in an official pi bond instead of a wannabe pi bond, which would look like this, where they're sort of evenly shared between those two carbons. So the product from attacking the beta proton is what we're going to call an elimination product. This reaction is going to be called E1 because all of this happens on the carbocationic intermediate And therefore, all of this is after the rate determining step of the reaction. All right. Questions about the consequences of the elimination reaction, what the product is. It's really, once you know what the orbitals look like for hyperconjugation, all you have to do is pop that proton off and make the electrons shift over, and now they're in their own pi bond. So the product of an E1 reaction is an alkene. We'll also sometimes call alkenes olefins. So what I'm showing you here, this is a question from home, do we get different products from attack of one of these orbitals versus the other? No. Technically, we're only attacking the Lumo, so I guess I shouldn't have drawn that arrow. I guess what I meant to communicate is we need two arrows for this process, and maybe we should put them in different spots, right? The nucleophile gets the proton, and then the electrons from that carbon-hydrogen bond shift over to form the new pi bond. We typically won't separate those out for elimination reactions. We're also typically not going to draw out all the orbitals. You're going to need to see that in your head going on, even though it's not written on paper. What we would draw as the mechanism for the E1 reaction after we form the carbocationic intermediate is remove the proton and make a pi bond. So the proton gets removed because you dump electrons into the LUMO. The pi bond forms because the electrons in the plus combination orbital shift over and make the new bond. All right, yeah.
When we talk about the rate determining step for the elimination one, EV1,
Yeah.
it would do the exact same as the SN1.
Yes, it would be. So the eliminations, I'm sorry, the rate determining step for E1 and SN1 is exactly the same. Remember how I told you when we drew our diagram that it was going to get worse? Let's try to show that. This will be fun. Nope, we didn't do it that day. Let's see, where did we do that strange and horrible? Ah, there it is, the lovely... a lovely energy diagram, which we are now going to make worser than it was. Okay, so yes, the transition state of the leaving group leaving to get to the carbocationic intermediate is exactly the same for SN1, and E1. So maybe we'll draw a carbocationic intermediate that has beta protons or whatever. Sorry, we'll just put C plus for carbocationic intermediate. At this stage, we're going to break off on another axis and say, aha, this axis will mean removal of beta proton and forming carbon-carbon pi bond. And that then competes with SN1, right? The purple line in the front represents going from the carbocation to the substitution product where we form a new bond between carbon and we'll say our nucleophile. In contrast, moving to the left from that carbocationic intermediate is going to be pulling off the beta proton and forming the new pi bond. So in reality, it's sort of silly to call this transition state 1 the SN1 transition state, because it's not. It leads to the carbocation. And then at that point, you have a splitting of the pathways where you could go down SN1 lane, or you could go over the E1 transition state. And we're going to see that because that choice happens after the rate determining step, there is basically no selectivity. In other words, we're not going to be able to, with any reliability, control whether once we get to the carbocation, it does SN1 or E1. So in general, and this is the thing that your text sort of waits until the end of chapter 8 to say, this is all making sense, but not so fast. SN1 and E1 always compete. Now, there are some texts in some classes where they try to make a distinction, and there are some practical situations where you probably can control whether you get mostly substitution versus elimination products from the carbocation. But for our purposes, any time from now on where you go to a carbocationic intermediate, you are going to be concerned about the possibility of both substitution, that is, attack at the alpha carbon, and elimination, that is, attack at the beta proton. They're always going to compete. Okay, so I guess over here we ought to put substitution products, and over here we'll put elimination products. All right. Questions so far? Yeah. Yeah, for our purposes, will we assume a 1-to-1 ratio? That's fine. We'll just be agnostic entirely about what the ratio is. We'll just say they're good, but they're both going to happen. We don't know to what extent. If you go in the lab and you do one of these reactions and you find a situation where, hey, I can get 90% yield of substitution product and the rest of it is just elimination products that I don't want, and I can separate one from the other, great, you got a good reaction. If in contrast you think you're going to do this reaction and it's a mess because you've got 2 to 4 different substitution products and as many elimination products, well, you're not going to be surprised and you're going to know why. Why is it? Because those two always compete with each other. Cool. What else? Yeah?
Wouldn't it be how good of a base it is or how much dependence it has also affect the result since one attacks the proton and one attacks the alpha carbon?
Yes. So what about, I mean, isn't it possible that how good of a base it is and whether it's sterically hindered or not affect whether we can get to the elimination versus substitution product? Yes, except that the nucleophile is not even involved in the rate determining step. And once you get there, the activation energy for the next step is small enough that the differences in nucleophile strength aren't going to matter. Now, the other secret we're going to tell you is that if you have a strong base, it's not going to wait around for the leaving group to leave. It's going to do E2 type chemistry. And if you have a strong nucleophile, it's not going to wait around for the leaving group to leave unless it has to, like if it's a tertiary nucleophile. Okay? And someone is asking, is there a reason why I drew the elimination products higher in energy than the substitution products? No, I don't mean to say anything at all about the relative stability of the elimination / substitution products. So whatever energy difference that appears to be there is not implied and shouldn't be interpreted as meaningful or anything you need to master. Okay, other questions? All right, so let's then talk about the aftermath of attack at the alpha carbon versus the beta carbon for the SN2 reaction. That looks so complicated, we're actually going to lose time by trying to copy and erase it. So we'll try again over here. Maybe, oops, what am I doing? So I'm going to draw the same alkyl halide. Here is the leaving group. Here's the other beta carbon. Here is the proton on the alpha carbon. Here is the sigma star or the Lumo that we've said is on the alpha carbon, but because of hyperconjugation, we're also going to say that it's on the beta proton and I'm going to draw here the minus combination where what's on the beta proton is out of phase with what's on the alpha carbon. I'm reminding you that this minus combination is the Lumo of our molecule. It might be helpful for the same reason to draw what the, what the plus combination would look like. The plus combination is not the HOMO of the molecule, but represents what happens to those adjacent carbon-hydrogen bonds because of hyperconjugation. And what that's going to look like is similar to what we saw above for the carbocationic intermediate. We're going to see spreading out of the carbon-hydrogen bond a little bit onto that neighboring alpha carbon. So you've got sort of, oh, I'm erasing, I want to be drawing. So you've got sort of partial pi bond character between those two carbons. And it's okay if you don't know how to draw this. I'm trying to represent what the plus combination would look like if you actually did the MO theory calculations. So this is the orbital that is filled. This is what's going on with the electrons that are in that adjacent carbon-hydrogen bond. They're delocalized a little bit out onto the adjacent alpha carbon. Okay? So think of this as spread out electrons from the carbon to beta carbon bond. Beta proton to carbon bond. And think of the upper combination as the spread out LUMO onto those adjacent beta protons. So again, if the nucleophile attacks at the alpha carbon, then the leaving group leaves and you get SN2 products. And again, remember that occurs with backside attack and inversion of stereochemistry. If in contrast we get rid of this here. If in contrast the nucleophile attacks not at the alpha carbon but at the beta proton, we remove the proton, and by attacking the LUMO we break the carbon bromine bond, and at the same time the electrons in that carbon-hydrogen bond shift over to form a new carbon-carbon pi bond. They already looked like a pi bond to begin with, but now they are a complete pi bond at that point. Now, I'm trying to just tell you what happens to the LUMO, how that explains where the leaving group goes, and then what happens to the electrons in the carbon-hydrogen bond. We're not ever, beyond this point, going to draw the mechanism of an E2 reaction like this. What we will do instead is just represent all of those arrows happening in the same concerted step. That is, your nucleophile / base attacks the beta proton, electrons from the carbon-hydrogen bond kick down to form a new pi bond, and the leaving group leaves. And the product you get from that, how embarrassing is that? I missed putting the hydrogens that are required to be shown when you write out a C. How embarrassing. Anyway, your products are the new pi bond that you made. The alpha carbon is now sp2 hybridized. You've made a new pi bond between alpha and beta carbons. the leaving group left, and you've got your nucleophile / base that's got a proton on it. Okay, and that is the E2 reaction. All right. So that's a lot. Questions you want to ask about that mechanism? Yeah.
So I assume that the SN2 and E2 compete just like SN1 and E1?
Yeah, so do SN2 and E2 compete just like SN1 and E1? Yeah, and if we were really ambitious, which I'm not sure how ambitious I'm feeling, probably less ambitious, what we would draw, why the heck not, right? Let's just give it a try. Let's have an axis going off into the distance. We're going to choose, I don't know what weird color we should choose, maybe this strange orange. It's going off into the distance in another direction. Now I think we're up to like 5-dimensional landscape. This will be break the beta hydrogen to carbon bond, make the new carbon-carbon pi bond, and a leaving group leaves all at once. And yeah, we would find, I mean, this is going to be kind of hard to draw, but we would find down here are elimination products. This is the E2 transition state. I guess I should have drawn it behind the SN2 words. You have to imagine that going off into the page. And how horrible is that? But yeah, just as SN1 and E1 always compete, SN2 and E2 sometimes compete. And there we will talk about when those situations are. All right? Other questions? Give us a hand. All right. So that's horrible, right? You didn't know the world could be so horrible, but it is. Yeah.
Looks like the E1 and E2 products would be the same.
It looks like the E1 and the E2 products would be the same. Yeah. I'm trying to figure out how. I mean, they. Yeah. Yes. In general, though, there are some nuances to that, so I can't just say yes. If there were a way to draw this so that the E2 and the E1 ended up at the same spot, yeah, we're really going to do it, aren't we? Okay. Fine. It's not your fault. I'm just like pretty pictures, so yeah, I suppose we could draw the line like here, and this, as we said before, this would be break the bond between the carbon and the beta proton, make the new pi bond, and leaving group leaves all together now. And that would look like so maybe that's more. I like that. It has a certain symmetry to it. I don't know. It's kind of horrible. So how are we going to judge whether we know that SN1 and E1 always compete, so that's easy. If the leaving group is going to leave, you're always going to have SN1 and E1 products. SN2 and E2 is a little bit more challenging to deal with. And so the way we're going to do this is we're going to group, as I said, our nucleophiles and bases, and this is, we're basically out of time, but we're going to group our nucleophiles and bases into 4 different categories: things that are good at both, things that are good at one versus the other, and things that are just terrible at both. And then when we interweave that with the kind of alkyl halide that you have, then the consequences of the reactions will be clear. Along the way, there's going to be a few principles that are probably just memorized details, but by the time we're done, you'll be able to predict the outcome of these reactions without a whole lot of trouble. So we'll just pause there, and we'll end just with that lovely view of the horrendous energy diagram we just made. See you next time.